This recording might come out a little shorter than average. I've got something else I need to do in slightly less than an hour, but we'll get as much of this done as will fit anyhow. Section 6 starts out with a discussion of power, which actually more logically fits in Section 5. Work, energy, and power are all related topics. But if I do it that way, Section 5 is a little too long and Section 6 is a little too short, so it's a timing thing. So I'm going to talk for a little while about power, and then the main subject of Section 6 is momentum and things related to that. But to begin at the beginning, the definition of power. Power means the rate that work is done. If you've got a friend that weighs the same thing that you do, and you're both standing at the bottom of a flight of stairs, one of you walks up the stairs, one of you runs up the stairs. By the time you get to the top, the same amount of work has been done, same amount of weight has been lifted to the same height, but the one who ran up the stairs did that work more rapidly, and that's more power. So in words, power equals the rate work is done. In symbols, rather than in English, first of all, average power work per unit time, or if you'd rather think of it in terms of energy rather than work, that would be the work energy theorem right there. Remember the work energy theorem? I was talking about it like all through the previous video. The work done on an object is equal to the change in its total mechanical energy. E equals, well, actually, if it's going to include all forms of work, this would have to include all forms of energy, not just kinetic and potential. But anyhow, the rate that work is done, or the rate that energy is delivered, or there's different ways of phrasing it, this would give you the average power during the time interval delta t. If the energy is not being delivered at a steady rate, then, well, it's the same story I've gone through a few times before. You have to take the limit. You have to let delta t collapse onto the instant that you care about. So instantaneous power would be the derivative of the energy, the rate the energy, a time derivative is a rate. Okay, if you differentiate with respect to time, that's the rate that something is happening. If I was going to spend more time on this, there'd be some homework problem where you have to use this, but you know, there's only so much time in a semester, and I'm going to kind of gloss through the discussion of power and move on to other things. Units to measure it in. The SI unit for work or energy is a joule. Time is measured in seconds. A joule per second is given a name of its own. It's called a watt. James Watt didn't exactly invent the steam engine, but he played a very important role in the development of steam engines. If you're using customary units, work is measured in foot-pounds and time is measured in seconds. So power would be foot-pounds per second. The British system, with its customary charm, doesn't give a special name to 1 foot-pound per second. You know, that would be like having 10 inches in a foot or something like that. 550 foot-pounds per second called a horsepower. And if you're asking yourself who came up with that, actually it was James Watt, as a way of rating the power output of the steam engines he was building. There is nothing inherently electrical about measuring power in watts. There is nothing inherently mechanical about measuring power in horsepower. It's just simply a matter of what's conventional, okay? It's customary to describe light bulbs in watts, and it's customary to describe car engines in horsepower. But if you wanted to, you could perfectly correctly walk into the hardware store and say to somebody, could you tell me what aisle I should be looking in? I want to buy a 1/10 of a horsepower light bulb. 1/10 of a horsepower, 75 watts, same thing. So one's a metric unit, one is a customary British unit. It's like giving your height in centimeters or giving your height in inches. An alternative formula for power from the definition, written just above it there, work divided by time. Well, work, by its definition, is the force times the displacement, the dot product of the force and displacement vectors. Just rearranging a little bit, stuck some parentheses into basically the same thing I'd written before. And I just did that to kind of emphasize this part of it, because displacement over time is the definition of velocity. So we will come over here. Power can also be calculated from force times velocity, or to be precise, the component of the force along the direction of motion times the velocity. Remember, a dot product has that cosine factor in it. So this the thing that was back over here, I guess I can still kind of do that. Work per unit time, that is the general definition. That's what the word power means in the first place. This comes from that and is applicable to mechanical type situations. This, for example, explains why heavy trucks always seem to go up hills so slowly, okay? If you're in a car and you come to a steep hill, most cars, I had a Chevy Chevette once, which was definitely an exception to this, but most cars have a lot of reserve capacity. You come to a steep hill, you just push down further on the gas pedal and the engine develops more power and up the hill you go. But you know, semis, especially if they've got a really heavy load back there, they're running much closer to full capacity. So if you, to simplify the discussion, if you want to think about a truck that's rolling along, putting out the maximum power that its engine can develop, and then it comes to a hill. Well, you've got a trade-off here. A certain amount of power can come from a big force times a little velocity, or a little force times a big velocity. Climbing the hill takes more force than just pushing yourself along on level ground. So as this goes up, that goes down, and that's why on steep hills you sometimes see the trucks with the flashers going, because they're under 40 miles an hour. So this is good for explaining that kind of thing. On the other hand, 60-watt light bulb, well, what you'd have to do is look at the light bulb from a mechanical point of view. You'd have to think about the individual electrons moving through the light bulb and what's the force on them and how fast are they going. And yeah, nobody does that. In the spring semester, when we get to electricity, we will start with the general definition, make some different substitutions, and get an expression for power in an electrical situation. Turns out to equal the volts times the amps. But, well, that's a story for another day. We're doing mechanics now. So, looks like it's time for the only example that I was going to try to do involving power. So you've got a crane lifting a piece of steel. Somebody's putting up a building and they're erecting the frame. And here's this, maybe it's an I-beam. And it's being lifted by a crane. So here's this cable that's attached. I'm not going to draw the crane and the guy sitting in it and all of that, but the part we care about is here's the cable that comes down from the crane, and it's lifting this thing. And there are two forces on that piece of steel. The cable pulls upward with some force F. And the beam weighs something. So there's the force of gravity pulling down. How much power does a crane have to put out? Well, you could do this either way, and it's roughly the same amount of work in both cases. You could figure out the velocity of this thing and go force times velocity, or you could work, I'm going to do it right straight from the definition. Power equals work per unit time, which, to repeat what I did a few minutes ago, the work is the force times the distance over the time. And the force, well, the question says the beam is being lifted at a constant speed. So because the speed is constant, the total force has to be zero. If the sum of the forces equaled something else, the beam would accelerate. If it's not accelerating, speed is constant, that means this force is the same size as that force so that they can add up to zero. So filling that in over here. And you know, there, as with many problems, there are several different variations in how you might want to look at it. Instead of saying work equals force times distance, you could say, since there's no change in kinetic energy, it's being lifted at a constant speed, the work done is equal to the potential energy that's being given to this as it's lifted. And then you'd call it mgh instead of mgs. Well, whatever letter you want to use for it. Newtons times meters gives you the work. So let's fill in the numbers. 1,000 kilograms for the mass. G is 9.8. And the thing gets lifted 20 meters in 10 seconds. So you multiply and you divide, and it comes out 19,600 watts. The question doesn't say what unit to express the answer in, so I would just stop at the first thing you got to, which would be this. But if it's maybe more meaningful to you if it's in horsepower, I'll sort of put that in parentheses. Or, for anybody who can't quite read that, the conversion factor is, if you round it off to the nearest watt, a horsepower is 746 watts. So 26 horsepower to lift it at a constant speed. Now you'd want to have a crane with more power than that, because for one thing, you need to get it moving in the first place. There's going to be a little while when this is accelerating as you first, as it picks up speed when you first pick it up. This force would exceed that force while that's going on. Plus, there's various sources of inefficiency in the mechanism, friction in the joints and that sort of thing. And so it'd take more than that, but that's a rough estimate anyhow. Okay, so that's about all the time I have to talk about power. Next thing down the page. Well, basically, it's just a little checklist of things I'm going to write on the blackboard. Impulse, momentum, stuff like that. As you hopefully recall, about a week ago, well, actually, it was less than a week ago I made the recording, but in your world, a week ago, if you're going along following the schedule, I started with F equals ma, and I made a bunch of substitutions into it, and I got the work energy theorem. Well, I'm going to start with F equals ma and make a bunch of different substitutions into it, and that goes like this. Summation of the forces, or the net force, whatever way you want to express that, is equal to an object's mass times its acceleration. And I'm not going to bother writing that subscript over and over again. Just keep in mind that this isn't one particular force, it's the resultant of all of them. And the other usual footnote here, if the acceleration is variable, you may have to let delta t approach 0, and this becomes the derivative of the velocity. But a equals delta v over delta t, possibly taking the limit of that. But I'm going to multiply both sides by delta t this time. Of course, delta v means v final minus V initial. And I can distribute the M across both terms. So last week, the result that I got to after manipulating F equals MA for a little while, was that force times distance equaled the change in the quantity 1/2 mv squared. This time, force times time is equal to the change in the quantity mass times velocity. Well, last week I said force times distance, we'll call that work, force times displacement really, and 1/2 mv squared, we'll call that kinetic energy. Well, continuing to sort of parallel that, let's give some names to these things. We're going to define force times time, that's called impulse. We'll use I for impulse. And momentum a choice of notation not nearly as sensible as I for impulse, but M is already taken for mass. Most textbooks use the letter P for momentum. Not exactly an obvious choice, since the letter P does not occur anywhere in the word momentum, but mass times velocity. And so what I showed a little further up the page here is that the impulse acting on something is equal to the change in its momentum. My computer keeps dinging. I think people are sending me emails. I should look at them at some point. Okay, so work is done when a force acts through a distance. An impulse is when a force acts through a time interval. Momentum is a stored up impulse in an analogous way to how kinetic energy is stored up work. Okay, something with kinetic energy is capable of doing that much work. Something with momentum is capable of exerting that much of an impulse. So there are comparisons, but there are also significant differences, not the least of which is notice all the little arrows over things. Yes, you had a break from vectors for a week, but they are back. Work and energy and power. Power is a scalar. Work, energy, and power are scalars. Impulse and momentum are vectors. So to illustrate that, kind of reinforce the vector nature of it, we've got, well, it's not too clear what these are. We have two things. If they were a little lighter, and if the masses were the same, I'd say they could be two balls rolling across a pool table. But, well, whatever they are, one's headed towards the left and one's going straight up. And I'm supposed to find the total momentum of this two-body system. So that total. By the way, be careful not to be messed up by the notation. P for power, P for momentum. Worst of all, I'm covering them the same day. I think actually power is a capital P and momentum is a lowercase p, but I don't know about you. When I write, big P's and little p's come out looking a lot like each other. I really should have covered pressure the same day also. That would just be perfect. And see if I could get all three of them in the same equation, maybe. So the momentum of object number 1 plus the momentum of object number 2 would be the total momentum of the entire system. Well, the 3 kilogram object has a velocity of 4j . Mass is a scalar, velocity is a vector. And we also have a 2 kilogram object. And it's headed toward the left. Its direction is -I. Well, I'm going to rearrange things a little bit just because I like them in alphabetical order. So 7 times 2 is 14, -14I for the x component. 3 times 4 is 12. As for a unit to measure it in, units of mass times velocity, kilograms times meters per second. This one actually does not have a name of its own. You know, like a Newton times a meter was called a joule. This lump of units doesn't actually have a name. So, you know, if you have any suggestions, send them in to, not to me, this is not up to me. I forget the name of the international committee that decides these things, but one thing that's a little more compact than saying kilogram meters per second is remember, impulse equals a change in momentum, so impulse and momentum have to have the same units. Newtons times seconds, force times time. That, I guess, sounds a little better than writing all of that. Perhaps the most important point here is just simply that the answer is not 26. Or if you include the minus sign, it's not -2. Okay, do not treat vectors as if they were scalars, because they aren't. Okay, there is no way to further simplify this than to just say this is the, unless you want to give the magnitude and direction, but that really isn't any simpler. If anything, it just makes more work for you. So this is the momentum vector. Well, let's see. A couple of examples, one example involving impulse and momentum before I go further. Number 3. So you're driving down the road 30 meters per second. That would be more or less throughway speed. And coming the other way is actually a whole gram would be a fairly substantial insect. That's not a mosquito. That's probably like a bee or a moth or something, dragonfly, something fairly large like that. But you and this insect have an unfortunate encounter. And to estimate the time it takes, all I did was I just said to myself, well, let's see, an insect that heavy, probably about that long, and how much, at a relative speed of 40 miles an hour, how much time does it take to go that far? And that's where I came up with the 0.002 of a second. So what we're after is the average force acting on the insect. Along the way, we'll determine the impulse. Well, actually, I'll determine the impulse. You'll just watch. Well, your first instinct might be to say, you know, people always just want to go right straight for the definition of a thing. The definition of impulse is force times time, but we don't know the force. That's one of the things the question asks for. But impulse is also equal to the change in momentum. And we have enough information to figure that out. Incidentally, I'm doing what I've done before, what a lot of people do when it's a one-dimensional problem, which is leaving out the little arrows over the top, because when something stays right on the x-axis, you're just dealing with numbers, basically. It's going to be the x component of the impulse and the x component of the momentum, and people don't usually bother to draw the little x's when all of the other components are zero anyhow. The impulse is equal to the final minus the initial. Momentum equals mass times velocity, and that's another one of those relationships you're supposed to know. If you look at your formula sheet, in the middle of a quiz to look up the formula for momentum, you're going to get this terrible sinking feeling when you look at where it says memorize formula for momentum. So momentum is mass times velocity. Mass. Now this is going to be the insect that we're applying this to. Question says find the average force on the bug. So the mass of the bug and then I usually stop here and look around the room and say, somebody tell me the bug's final velocity. And sometimes somebody gets it and sometimes they just kind of look at each other. But after the collision, it's stuck to the car, okay? It's kind of in a rearranged form, but it's stuck to the car. The car will not have slowed down significantly. I mean, if you want to work to a lot of decimal places after the collision, the car is going slightly slower. If it was exactly 30 meters per second before the collision, maybe it's 29.999 something now. But to an ordinary level of accuracy, the car's speed is not noticeably affected by running into an insect. And the bug is stuck to the car, so the bug is going 30 meters per second after the collision. 0.001 is the mass before the collision also. Momentum is a vector. Even in one dimension, you have to pay some kind of attention to the directions. A popular mistake would be to leave out the minus sign. After the collision, it's going to the right. Before the collision, it was going to the left. So minus cancels minus, and you'll end up adding. That was one of the things it asked for. Find the force acting on the bug. Well, I've got a number to stick in for I now, and I've got a number to stick in for delta t now, and we'll solve for F. Two thousandths of a second, that was given in the question. 0.04 was the answer to the first part of the question. Divide both sides by 0.002. Which is actually not that big of a force. It's only around 5 pounds, a little less than that actually. But, well, in the first place, it's only, well, this is the average. The force would kind of, at the very least, the force would kind of build to a peak and then taper off again. It might even vary with time in a more complicated way than that. The peak force is probably somewhat more than that. But I guess the main thing is, first of all, an insect is not as rugged as an elephant. It doesn't take as much force to hurt one. You hit an elephant with a fly swatter, you know, and it's going to be fine. I'm not sure you're going to be fine, but it'll be fine. The other thing is this 20 newtons is distributed over quite a small area because insects aren't very big. And so even though it's a relatively small force, there's quite a bit of pressure there. So it does not go well for the insect. Next thing as we work our way down the page. This seemed to me like a good time to bring up Newton's third law. A couple of weeks ago, I did a whole unit on Newton's first and second laws, and I said we'd get to the third law another day. This may seem to you like sort of a random place to throw it in, but not to me, because slightly further down the page, well, no, I guess it's on the next page, but sometime pretty soon, we're going to get conservation of momentum. And Newton's third law and conservation of momentum are kind of just two different ways of looking at pretty much the same thing. But as far as what it says, the third law says forces always come in pairs. That's related to the fact that the objects exerting the forces always come in pairs. You're never going to be walking down the hall late one afternoon, and all of a sudden you get knocked over on your face and, you know, your books fly everywhere. And when you turn around to say something, nobody's there. That would be spooky. If you got pushed, somebody or something had to do the pushing. There are always two objects involved in any force, the thing that did the pushing and the thing that got pushed on. And the third law says that anytime this is happening, it's a mutual interaction. Not only does A push on B, but object B is simultaneously pushing back on object A. And these forces are the same size, opposite directions, but the same size. So if it was a 40-pound force that knocked you over, then the person who ran into you also felt a 40-pound force from you. The fact that you fell over and the other person didn't is not because you had a larger force acting on you. It's simply because the other person was balanced better or braced for it better. But if the other person pushes you with 40-pound force, you push back on them with a 40-pound force. If A exerts a force on B, B exerts an equal and opposite force on A. These two forces are often called an action-reaction pair. For every action, there's an equal and opposite reaction. So here's a quick example, just a picture. Somebody, and I'm going to have to wrap this up pretty soon and check all those emails, but somebody kicking a soccer ball. Obviously, your foot exerts a force on the ball. That's sort of the whole point of kicking it. But as you might be aware, especially if you try kicking it barefoot, the ball pushes back against your foot also. If you pay attention, it'll feel kind of like the ball is slapping your foot. Or maybe think of it this way. What if you were standing on a skateboard? Now, I'm not sure, kicking something while standing on a skateboard sounds a little tricky to me. I would rather throw it than kick it. But if you're in some sort of frictionless situation, like standing on a skateboard or sitting in a canoe or something like that, and you throw a heavy object in one direction, as soon as you throw it, you are going to start drifting in the other direction. Your skateboard is going to start rolling backward, okay? So that's from the reaction force. You push on the ball pushes back on you. Some further examples. Because I have found Newton's third law is often a misunderstood thing. Yeah, that's about where that goes. We have a box pushing down on the floor in some sort of a little room. Actually, the little room is an elevator. But let's see. A is the force of the box. Okay. Bottom of the box pushes down on the floor. B is the floor pushing up on the box, the normal force, except I called it B instead of N this time. When the elevator is in equilibrium, A is equal to B. So if the box is a 20-pound box, both of these forces are 20 pounds. How do A and B compare when the elevator is accelerating upward? I'll give you a moment to think about it. Try and come up with your own answer because, well, as you've maybe heard me say before, most of the things I know, I learned by doing them wrong. So you do this and then I'll tell you why you're wrong. Or maybe if you're really smart, you'll be right. That happens sometimes too. The answer is that they are equal. Write that down. I suppose you've got it, but if I write it down, that improves the odds that you'll write it down. They are equal because of Newton's third law. They are an action-reaction pair. they fit the description where it says A exerts a force on B, B exerts a force on A, the box exerts a force on the floor, and the floor exerts a force on the box. The fact that the elevator is accelerating is irrelevant information. It has nothing to do with the third law. It's all kinds of important for the second law, but I'm not talking about the second law right now. I will be in a minute, but they are equal because they are an action-reaction pair. Now, if the question doesn't ask for this, unless I skipped over something. Now, it doesn't ask for this, but it's a good point. If the elevator is accelerating upward, the normal force is more than the weight of the box. Okay, so here's the box, and the upward force on the box was B, and the downward pull of gravity is mg. So if it's lowercase a for acceleration, if it's accelerating, B, the normal force, is greater than the weight of the box. That gives you a net upward force that makes the thing accelerate. Like I said before, all of that has absolutely nothing to do with the third law. This force B is equal and opposite to the force of the box pressing against the floor. Get to the bottom of the page, and I think that's where I'll divide this, the rest of section 6 later in another recording. Example, the reaction to an object's weight. As I stand here, the earth is exerting a downward force on me, 180 pounds, okay? That's what I weigh. Maybe a couple more because I just ate lunch a little while ago. But, you know, I asked the class, what's the reaction force to my weight? And more often than not, somebody gives me the wrong answer, even with the right answer, looking up at them from this handout right in front of them. They always say, well, that would be the normal force. There's gravity pulls down on you with a 180-pound force, and the floor pushes back up with a 180-pound force, equal and opposite, right? They are equal and opposite because of Newton's first law, not the third, okay? As I stand here without moving, I'm an object at rest, remaining at rest. Therefore, the forces on me have to balance. But notice, the reaction to a force on object B is not another force on object B, okay? The reaction to a force on me is not another force on me. The third law is all about how two objects push or pull on each other. Keep that phrase "on each other" in mind, because that's the essence of the third law. So because I'm in equilibrium, the forces on me have to balance, and therefore the normal force is equal to my weight. If I was not in equilibrium, like, remember the accelerating elevator, just talked about it a minute ago? The normal force would not equal my weight if I was standing in an accelerating elevator. They are not an action-reaction pair. The reaction to my weight, well, let's fill in some things in this general statement here. The gravitational force on me comes from the earth. So if the earth exerts a force on me, then I exert an equal and opposite force on the earth. You see, I have a gravitational field too. Gravitational attraction is an inherent property of matter. Every object in the universe attracts every other object. So I weigh 180 pounds in the Earth's gravitational field, and the Earth weighs 180 pounds in my gravitational field. On the one hand, the Earth, I'm a lot less massive than the Earth, but on the other hand, you know, the Earth's field's a lot, maybe I should go at it this way. The Earth's field's a lot stronger than mine, but on the other hand, there's a lot more of the Earth to attract than there is of me, and the two things even out. If you want to go at this from an experimental point of view, go home, get your bathroom scale. First of all, stand on it. And in my case, it would say 180 pounds. And then just take your bathroom scale and flip it upside down. You'll have to figure out some way that you can read it with it flipped upside down like that. But now you've placed the Earth on the scale in your gravitational field. And if you can figure out some way to read the display with it turned upside down like that, you'll find it reads the same thing. So things to keep in mind when people ask you questions like this. Action does not act on the same body as the reaction, okay? The reaction to a force on me is not another force on me. Here's the Earth and I attracting each other. And now, 180-pound force on the Earth, it does not have any measurable consequences. But if it's the Earth and the Moon pulling on each other, it's very definitely measurable that they are free-falling objects in each other's gravitational fields. Anyhow, action and reaction not on the same body. Also notice both are the same kind of force. The reaction to a gravitational force is another gravitational force, not a contact force. Okay, going to leave that there and get back to you later.